Hello, and welcome to this JUMP Academic webinar, Designing and Analyzing Experiments, Part 2, Advanced Topics. I'm Ross Matusalem, a JUMP Academic Ambassador. I'm just here to host today, and I'll be answering your questions in the Zoom Q&A throughout. My colleague Volker Kraft will be presenting today, and his presentation will follow on the academic webinar from 2 weeks ago, Designing and Analyzing Experiments, Part 1, that introduced some basic topics like the design and analysis of one-factor and factorial experiments, and also sample size and power calculations for one-factor experiments. So today, Volker is going to carry on from that introduction and introduce some more advanced topics and the relevant tools and techniques in JUMP. Before we get going, I want to encourage you to ask any questions you have throughout in the Q&A panel in Zoom. You can see the little icon there on the slide. So please type any questions you have into the Zoom Q&A, and I'll do my best to answer them as we go along, and we may have some time during the middle and or at the end for Volker to take some questions live. I do also welcome you to use the chat for any general comments to us or to the group at large, but again, please do put those questions into the Zoom Q&A window. So with that, Volker, are you there? And if so, go ahead and steal that screen share.
I'm here. Thank you, Ross, and thanks to everyone for joining or watching this webinar. I am so excited knowing from my many years working for the JUMP academic program that we will see the methodology and tool set for problem solving and driving innovation in many industries. And furthermore, learning about strategic experimentation is so critical for students in sciences and engineering and other disciplines that getting access to modern DOE in JUMP without the need for any line of code will be a huge advantage for their careers. During our previous webinar, Introduction to DOE, Part 1, my colleague Kevin Pockner did a great job introducing you to some introductory topics of experimental design. He listed a broad range of resources which are all online and available for learning and teaching DOE. Experiments with a single categorical factor were explored to understand the underlying statistical concepts like analysis of variance. So here we see an ANOVA table for a single categorical factor at 4 levels. A fractional factorial screening design was demonstrated as a classical design, which is also a nice example for teaching DOE, but I think not seen so much in practice anymore. So looking at the result, here we see a surface plot from this experiment. Especially for DOE beginners, and a bit as a cliffhanger for our session today, Kevin showed Easy DOE, which is an easy-to-use interface to the custom designer, covering all stages end-to-end, from problem description to reporting results in a single JUMP platform. And in case you missed Part 1, you can also watch the recording and download Kevin's journal at the link given here in my journal, which will also appear on the JUMP user community after the session. So, what can you expect from our second episode? We will see a number 1 JUMP platform. So as a JUMP user, you probably know that most of the magic is happening on the Analyze, Graph, and DOE menu. And the first analysis platform, distribution, is a mandatory step for most data explorers and analysts to look into distributions, univariate outliers, normality, or confidence and prediction intervals. Graph Builder, the first option on the graph menu, is the most versatile data visualization tool in JUMP. All kind of graphs built just by drag and drop. And today, you will understand why the custom design platform is the #1 option on the DOE menu in JUMP, followed by augment design. And we will see why and how to use these modern DOE platforms, also followed by some tips and best practices today. So during our live demonstration today, we will build a modern design with a mix of factors and different factor types. And we will see what we can learn from such a flexible design. And we will explore and also model the experimental data from this experiment later. Okay, let me take you on the journey from classical design to modern design. So classical DOE, like fractional factorial, full factorial, also some examples were shown by Kevin last time, basically fit your problem to a classical design, or you have to fit your problem to an available design, which is typically taken from a catalog with pre-built designs like templates. So that means that choices are limited. Maybe you can specify the number of factors and a few factor types, but you are not really flexible. So the number of runs are typically given, predefined by each design. So here you are not flexible at all. And when it comes to real world requirements like constraints and hard to change factors, it's typically game over unless you want to fit your problem to a design available. So for modern DOE, you can fit a modern design to your problem. That's the other way around. So this works because the design is generated for you by the computer, a software like JUMP, on the fly. And the design will be optimal for your problem. And we also talk about optimal DOE. So this is a fixed term, and we will also come back to this later on and learn what optimal means. And these designs are extremely flexible, especially if you use a tool like the custom designer in JUMP. Some users told me this is the most flexible DOE tool available. And we will see it in a few minutes. And optimal designs, computer-generated designs, are also based on a model. So you have to specify a model in advance before the experiment. And that's the reason why these type of designs are also called model-based designs. And you also find this term in the literature. And everything, all this flexibility, everything is built into a step-by-step design platform in JUMP, which works like an assistant or a wizard. which walks you through the problem, and then you tell the computer about your design and your requirements. Yeah, so you guide the software. You don't need to code anything. And you also don't need to know about all these classical design types and the differences and when to use which one. Yeah. You just tell the software what's your problem, what are your goals, and then the software will do all the magic. And also all the statistics behind the scenes. Yeah, for instance, if your temperature is not easy to change in your experiment, let JUMP know, and JUMP will use a split plot design. Or if some model effects are not necessary to estimate, but just nice to have, let JUMP know, and it will use a Bayesian design approach. And if you add a random blocking factor for some reason, JUMP will prepare a linear mixed model using RAML, restricted maximum likelihood, a special modeling technique for an appropriate automatic analysis as soon as all data is available. So I really like to think about a JUMP user like a conductor, yeah, orchestrating all the musicians, mastering different instruments, and producing the most enjoyable piece altogether. Yeah, and in our case, this piece is the most efficient learning outcome from an experiment. And today, the demo I want to show you is a conductive polymer experiment. And many kudos go to my JUMP US colleague, Scott Allen, for sharing this example. So in this experiment, we have a constant polymer powder, and this is blended with some mixture components. And here you see that we have 3 mixtures. And what's special is that the sum of these mixtures, because they are mixtures, has to be constant 100%. And we also work at a continuous temperature and time, so 2 continuous factors. And the output of this system is also radiated with light at one of 3 wavelengths, yielding a conductive polymer composite material as output. So let's start to create the design for such an experiment. The first step, using the custom designer from the DOE menu, the first step, let me increase this a bit. First step is always about the response. So that's what we really care about. So the response, in our case, the response is the damping. And we want to optimize, that's the experimental goal, and maximize the damping by setting the inputs our factors. And setting the factors, that's the next step. Yeah, and you see the table on my JUMP journal. So all factors as maybe described during a brainstorming with some polymer experts are given on this table here. And note that we have a combination of different factor types. We have a constant, we have 3 mixtures, we have 2 continuous factors, and we have a categorical factor at 3 levels. So what could we do if you would start with a classical design? So like classical factor screening, a screening design. Yeah, so you see that we have the choices for continuous, discrete numeric, and categorical factors, but no mixtures. What about another classical design, maybe a response surface design? So here, even worse, we only have continuous factors available. So maybe you saw that there is also a mixture design. Is this a good option? No, sorry, here we only have mixtures. So for the combination of all these factors, if we don't want to split the experiment into separate experiments testing subsets of our factors, if we want to run them all together, we need a more flexible design tool like the custom designer. And here we could start to add the factors manually. So we have 3 mixtures. And you see the flexibility you get from this menu alone, the factor types. 3 mixtures. We have 1 categorical factor on 3 levels. We have 2 continuous factors, temperature and time. And now I would also enter the names of the factors and the ranges manually. But let me remove everything because we also have this factor table here. So with such a table, setting up all the factors, we can just load the factor definitions from that table into the design tool. So we don't need the factors anymore. Let me minimize them. Okay. And so now you see we have all the factors set up. So the first step was the response. Now we didn't set any spec limits. We could also have multiple responses for a multi-response optimization. That's not the case. Just a single response we want to optimize. Second step was this factor specification. The third mandatory step, setting up an optimal design, is this here, the model specification. So this is the a priori model, listing all the model terms we want to estimate after the data collection. So when we can fit this model to the factor and measured response data. And on the first hand, the model must support our experimental goal. So what is the goal of our experiment? It could be just a screening experiment, and that's what JUMP assumes by default. So here we have main effects only. And this corresponds to a simple screening experiment to find the important factors from this set of all the factors we currently have on our radar. We could add more model effects, also higher order effects, and with the response surface model, we could also do an optimization or a tolerance design. So this could be another goal. A tolerance design is typically used to study robustness. So here, let's go with a screening setup. And for this very simple model, we have 6 main effects, plus the powder, the constant, or the intercept, which is always there. So we have 7 estimates to determine. And this is the minimum of data points we need. And these are the unknowns. And this also corresponds to the pieces of information we need. And the pieces of information, statistically speaking, these are the degrees of freedom. And if we want to learn more, if we have to estimate more parameters, more model effects, we need more degrees of freedom, more data. We have to measure more response data. So that's the currency in experimentation, which is the number of runs. And as I said, the minimum is 7. There's a default suggested by JUMP. And this is typically 4 or more runs more than the minimum, because we also want to estimate the experimental error. And that also needs a few degrees of freedom. So we need some more data than the number of parameters on our model terms. So the recommended number is 12 right now. Our budget covers a maximum of 24 runs. So we also know that there could be, let me go up, an interaction between temperature and time, and there could be also some curvature for these two continuous factors. So here I add a 2-factor interaction for these two, and I also add the power terms. I get a warning about the mixtures, but that's fine. So now we also have, so we added 3 model effects to our list. So we also know that there could be some interactions between the mixture factors. And we are also interested in a 3-level interaction between all our mixtures. So I select them and interactions 3rd order. And now we have some more model effects. So 4 more in this case. And now the recommended number of runs is 18, 4 more than the minimum 14. If we would say, sorry, we can only do 16, that's another flexibility you have. You could say, no, sorry, we can only do 16, and then you will get still an optimal design, but just with 16 runs. In our case, we are lucky we can afford 24 runs. So all of this is a bit like negotiating with the software. So finding a trade-off between what we can take away from the experiment, what we can learn, and the cost, which is the number of runs. As soon as you are happy with this negotiation, you would say, okay, let's go and make the design, and let's have a look at the design. And by clicking Make Design, now JUMP starts to search for the optimal design. And what does optimal mean here? So this can be set as an optimality criterion. And the default is recommended. And recommended means unless you have a full response surface model, which would trigger an optimal design. And this is for minimizing the prediction variance. So this is really for optimization and a precise prediction, precise as possible. Other designs are typically set as a de-optimal design. And here you want to learn about the system or the process. So we want to minimize the standard error of our parameter estimates. And that's probably set for this design as well. We can check this under design diagnostics. Yes. So this is a de-optimal design. We can preview the design. So that's maybe not that spectacular. More interesting are the diagnostics. We will see some examples later on. But now we can take the final step and make the table to get ready for the actual data collection. And you see randomization, that's a no-brainer. So you always want to randomize the runs to average out lurking variables, which could have maybe an influence on the damping, and we don't know about them or we cannot control them. So what can we do? At least we can randomize the runs. That's a best practice in any case. So let's get the table. And this is the table, our design or test plan we can take into the lab. And these are the runs from the 1st to the 24th run. We see all the treatments we have to configure. We have to control on our inputs. And then we have to measure the output, the system output, which is the damping, and we have to enter the measured value to, in the response column 24 times. So what we also have here is some metadata in addition to what you see on the table in the cells. The columns have some properties. So the damping remembers that we want to maximize the response. So how to know this at the end when we have the model and then click optimize. Then Jump will look here and see optimization means maximize the output. There are other properties on factors. So here we see that this is a mixture factor. We also see that this factor is easy to change, and everything what we specify during the design is not lost, but saved as metadata on this table. And we also have some table scripts, so we can go back using the DOE dialog. So if you close the dialog, you can click the green triangle and then walk back to the first step, setting up the response again. If you changed your mind, you can redo and go back. And we also have analysis scripts saved here to go forward and run the analysis. And clicking model, that's fitting a model. And we cannot do this yet because here we don't have the response data in, but you see this model, this is exactly the model we specified during the design, the a priori model. Now it's after the data collection and we are ready to fit a model. Not with this data set, because we need the response data. And we have it here. So that's the link on the journal. So this has the same design, the same data set, basically, but the response has all the data added here. And we can visualize and explore this experiment now. So we can look at the response, which settings gave us the highest damping at the system output. And we see that it was not the low wavelength. It was not the mid temperature. And we see that highest temperature is most promising, just following the interactive data visualization on the distribution platform. I could run a predictor screening just using a bootstrap forest to see a ranking of our factors. And we see that the wavelength is most important for building a forest, a bootstrap forest. And this organic mixture is least important. And of course, we can also build a model using multiple regression. And what we typically want to get to is the profiler where everything happens, our understanding, system understanding, where we can see the relationships between inputs and outputs. I just remove the desirability information, and now we see the traces between our response on the left, damping, and then we have the three mixtures, and we can change a mixture. You see the other two mixtures have to change as well because the sum has to be constant. I can change the temperature, also look at different wavelengths. What if the wavelength would be L2? It looks promising. It seems to have the highest damping. And finally, the optimization is just one step away, maximize desirability. And that would be the solution. So the solution suggests to set the system to the highest temperature, the lowest time, wavelength. Now it's level 1. So this is due to some interactions going on. So it's not that easy to read. You really have to get the full picture. But that's easy also with the latest features on the profiler, so you can add data points and interactions. We don't have the time to look into this, but I really invite you to try this out on the latest version of JUMP version 18. Okay, so that's the model. Let me close this again. Ross, are there any questions about this demo, this example?
Oh, we've had them all answered in the Q&A, but perhaps right now you could comment, because I imagine it's relevant to a lot of folks, just exactly how mixture factors work and what makes them different from your traditional continuous factors.
Good question. If you look at the design table, they don't look special here. What's special is that the sum of the three mixtures has to be a constant sum. And if I select them and let me get the sum. So this is the result. So you see that the three mixtures sum up to 1 for all runs. So the condition is met for all runs that the sum is constant 1 in this case. So there's an advanced option where you can also set this sum using the design tool, and that's the mixture. There are also special tools, ternary plots, and special visualizations to look at mixture factors, but this is beyond the scope of today's webinar. But we also have dedicated tutorials, webinars, and also trainings just about mixture experiments.
Great, thanks, Volker. I think we've handled all the other questions all right in the chat, so we can keep going.
Okie dokie. So what's left is that we didn't touch everything on the custom designer. So there are some other important settings we didn't use. So I want to at least point you to them and make you aware. And then the final section is about a handful tips and best practices I also want to mention in addition to the custom designer. So custom design features. So 5 features I think have to be mentioned. Blocking. This is one of the fundamental design principles also developed by Ron Fisher more than 100 years ago. Yeah, and blocking does some grouping of the runs so that the variation within a group is smaller than the variation between the groups. Yeah, so we get some more homogeneous groups of runs. And a classical example is the day-by-day variation. And using, let me get the custom design back. So using the custom designer, you basically have two ways to set up a blocking factor. Yeah, one option, the first one is to have a blocking factor, a factor type blocking. Yeah, and this is a fixed block effect. Yeah, because you will learn about the signal and all the different days in this example. The drawback is that this needs the number of levels or the number of blocks -1 as degrees of freedom. So you need a lot of data just to estimate the signal for this blocking effect. And you will learn about the difference between all these days. Not sure if this is needed. If not, the alternative is a random block effect. And this can be configured down here at the design generation step. So you would activate this, and this would be called a random block effect. And the random block effect just estimates the variance, a variance component which can be assigned to the block effect. So just a variance, and that means that you only need a single degree of freedom for this random block effect. So it's less costly, but the analysis needs a mixed model. And on the analysis side, it's a bit more complex also to read and to interpret, but it's automatically set up by JMP. You just need to run the model script, and then you will get all the results and can learn about this variation. A bit more advanced and sophisticated is another type of grouping, and this grouping is called grouping into plots. So not blocks anymore, but plots. Yeah, so then we talk about whole plots and subplots. Again, we are grouping our runs. Yeah, and this can be done by setting a factor as hard to change. Yeah, and this would group all the low temperature runs and high temperature runs together. So the advantage is you don't need to change the temperature all over again and again. Yeah, in this case, just once if you have two levels. So this hard to change factor experiment, it's called a split plot design. So this could be motivated by a factor which is really hard to change, like the temperature. Yeah, so then it's driven by the experiment itself. Or it could be also be driven by the process setup. So you could also have a plot per batch, so a grouping by batch. If you produce outputs in batches, you could group everything together by batch. And then it's always about two different variances. The variance between the groups, between the plots or whole plots, and the standard variance between all the runs. And there's a ratio which is important and also good to set, and under advanced options, you have this split plot variance ratio. And this is the ratio between the whole plot variance to the run-to-run variance. And this can be determined using some other data or calculations, and then you can set it there before creating the experiment. Next one is about constraints. So this is to fine-tune the factor space. Maybe you want to exclude some disallowed combinations or treatments, combinations of factor settings. So in this example, maybe temperature and time should not set to the high level at the same time. And then you can set up a constraint. But I see that there is a question. Ross, do you see it as well? So there's a...
Oh, sure. Somebody has their hand raised. If you have a question, please do type it into the Q&A and we will address it there. Thanks.
Okay, so for these constraints, so they can be set here. You have different ways to do this. In any way, it's a good idea to define the constraint before you run the experiment. Don't ignore this, and then during the experiment you will see, oh, temperature and time, we cannot do this. It's the run number 19. Let's skip it. Then you will have a missing value on the design table. And this could break your model. So it's a model-based design. Typically, we need everything. We need all the data points to fit the model and to get to the quality and the diagnostics we could evaluate before the experiment. We need all the data. So if you cannot get some data, cut off that factor space by linear constraints, or you can have simple filters. They can easily be set up to define the disallowed combinations, what you want to exclude. And if you are not able to set maybe some complex constraints, maybe using some formulas or anything, there's a very powerful method with no limitations to set constraints, and this would use the covariate and candidate runs. So what are covariates? Covariates are typically factors which have an effect on the output, on the response, but they cannot be controlled. And an experiment, it's a multi-factor experiment. You have to control all the factors in your experiment. If some are uncontrollable, so what can we do? In the case that the factor is unknown, maybe humidity. You cannot control the humidity in your lab, but it may have an effect. So what we can do at least is, during the experiment, the data collection, measure the humidity and add the measurements as a covariate factor. So this is a factor type, as a covariate factor to our experiment. Another use case is when we know the values in advance. So again, we cannot set them, but we are in a lucky position that we know about the values. And maybe we have 200 samples on store, and all of them have some specific properties, a density, a weight, a pH measurement, and so on. And we only need 24 for our experiment. So what is the best subset? In this case, you point jump to the inventory, the candidate runs with the 200 samples, and JUMP will pick the best subset of maybe 24 which are needed for our experiment. Yeah, so to get an to optimize the experimental setup by choosing the best subset. And the last use case is, again, we know about the values of our covariates in our candidate set because we simulated them beforehand. And that means that you can simulate a huge data set, maybe with thousands of values or also covariate factor combinations, the weights and the densities and everything, all the properties or what you simulated. But into the simulation, you can build your constraints. Yeah, you can simulate data using any formulas and any complexity, and you don't simulate a factor combination, which is disallowed, of course. Yeah, and then you will have maybe thousands, 100,000 of allowed treatments, factor combinations, and then ask JUMP to pick maybe the 24 best runs from that huge inventory for our experiment. This is a bit a different way to find the optimal design. It's not swapping the individual cells anymore, the levels on a factor back and forth, and then searching for the optimal design. So this is really run based. Yeah, you take a full row from your candidate set, a full row or not. It's row based, not cell based anymore. But it works perfectly, and you can also visualize what happened. And with this, you can have any constraints built into your simulated candidate set. The number of starts and the search time, these are two little small settings. You can also find on the top red triangle, number of starts. You can start the search several times, and the default is just one. Maybe you want to search multiple times, and maybe you also want to spend some more time searching for an optimal design than just 10 seconds. Yeah, and if an individual run or measurement really costs a lot of time, a lot of money, it could be a good idea to spend some more minutes or even hours in JUMP searching for an even better design. So if you are lucky, you may save a run or two just by a more extensive search. By the way, all of these features and settings, they all have links which send you directly to the online help, which explains all the details, gives you examples. And there are even some more examples down here. Different examples for using the custom design tool. And they can all be found in the documentation, and the JUMP sample data also comes with data sets and measurements, so that you can also look into the designs, but also the analyses for these different cases, looking into blocking and covariates and basically all the topics we mentioned so far. So for them, you will find an example in the documentation. As I said, DOE is a key application area in JUMP, and the custom designer is the way to go. If you need flexibility, that's the way to go. And I think the custom designer is also the by far most popular design tool in industry. Yeah, so classical designs, maybe a mixture, but custom design, that's the most flexible design tool you can get. Okay, just to close this here, some other remarks and pointers. Center points and replicates. So if we go back, design generation, center points, replicates. So you can set typically both of them, a number of center points, and in addition, also a number of replicate runs. But by this, you're really forcing the design tool to add these runs. Yeah, and you are limiting the flexibility of the search for the optimal design. The reasons to do this, yeah, for replicates, you can use them to estimate the pure error, and that's good for a lack of fit test. So if you want to see if we are missing anything in our model, maybe it's not just a noise, but there's really something systematically missing in our model, and that could be found doing a lack of fit test. And for that, we need measurements about pure error, and replicates are the way to go here. Center points, so they help also to look into an evidence for curvature. So are all the factors linear? Do they have a linear relationships, or could there be some curvature for some factor? A center point, a global center point, could tell you about this evidence, not about the factor which may have the curvature. If you want to get this all in one go, look at the definitive screening design. So this can help you here to find a curvature on a specific factor. But I also know some experts who say, don't set replicates, don't set center points. Let the search do the job and find the best, the optimal design for you. Because if you take some runs for these, you may not be able to estimate all the parameters anymore, or not at the same precision or quality. So you will lose something. It has a cost. It's a trade-off. Design evaluation comparison. So that's a good idea. So to look into the evaluation, and we can look at the design again. Yeah, so we could spend hours just talking about the ways how to evaluate a design before we actually run the experiment. So it's good to know about what can we expect. And that's also a strength of this method, because everything is predictable. We will know exactly what we have to invest, what we have to spend to learn something and to get a specific output, learning output. Yeah, it's not just try and error and good luck. No, it's really predictable. Yeah, and here you can see what we can expect. Yeah, so I missed the interactions in this case, but yeah, we see the power, and we can see that the power for the mixtures is lower than for some other factors. Yeah, we can also look at a correlation, a color map on correlations. So this is about aliasing. Yeah, and aliasing means that there's some smearing, that you cannot assign an effect you observe on the response to one specific effect. Yeah, so here, if these effects are aliased, and they are totally aliased, the correlation is 1. So that means that we cannot disambiguate between the third mixture factor and the interaction between the first and the second. So for mixtures, there's a significant aliasing in this design. And there are even more diagnostics. Yeah, and comparison, so that's nice. You can also compare designs side by side, yeah, and load different designs into a comparison tool, and then that also helps you to select the best design. Design Explorer, this is very similar to model screening. So you can quickly explore different design choices for different numbers of runs, maybe different optimality criteria, and then you see all the efficiencies, you see the prediction variance in an overview, and then you can pick the best design. So you can really scan a bandwidth of different designs really easily using the Design Explorer. Sequential experimentation, that's last but not least, a best practice. Don't think about a one-shot experiment, one huge experiment to answer all your questions. No, it's typically a step-by-step approach. And then you start with a custom design tool, and you get an optimal design first experiment, and then you add some more data, maybe to learn about some other model terms. Or you want to expand your factor space because the first experiment pointed into a direction where we can expect some even better conditions. Or you want to disambiguate between different model effects, which were aliased in the first experiment, but we accepted that because to reduce the first experiment. But now we want to know, is it this main effect or this interaction? So let's add a few more data points, and we don't need to ignore or remove the available data. We just keep everything and then add some data points and get another optimal design to answer some more questions. And the last comment is that so far we talked about model-based designs. So the custom designer needs a model specification, it's model-based. That can be a problem. So as I mentioned, if you expect some missing values from your experiment, it could break your model. And then you are not able to analyze your experimental data. Or the underlying model is so complex that you cannot really map it to a list of model effects. And in some situations, there's no random element. So if there's a mechanistic or deterministic problem, there's no random variation anymore between runs. So you can forget about blocking and randomization and everything. So these are computer experiments, which are typically done using a space filling design. And this distributes the design points typically uniformly or other strategies over the factor space, and methods which are quite popular here are Latin hypercube, Gaussian process, and a few others. Yeah, so this is a model agnostic. You don't need a model anymore. It's a model agnostic approach, space filling designs, and they can be found under special purpose space filling designs. And again, a pointer into the documentation if you want to look into this. For you, when you get the journal, there's even more. So the big picture, there are more capabilities for DOE, but there are also more capabilities around DOE for some specialized modeling, screening, reliability, capabilities which are also DOE related and helpful for experimentation. They are all in JUMP. So it's not just a DOE package. There's much more you probably can use beneficially. As I mentioned, Kevin listed some resources during his webinar. I just added 3, so I have some pointers into the documentation. I also want to mention, if you're interested in custom DOE, we have a full training course, typically a 2 days training course, published as an e-learning course you can use on demand on the user community. Yeah, here's the link. So follow the community, and then there's a learning space, yeah, Learn Jump. And there look up the on-demand courses, and this is the course just about custom design. And this is really a deep dive, also statistically, the most detailed training content available. I know about focusing on the custom design. And then networking and reading about discussions between different experts in this space. The user community. If you register, you can also start your own discussion. So you're not alone. And we are also here to help the JUMP academic team. Here's the contact form. Please reach out to us if you are interested in integrating JUMP into your course or teaching a workshop or to your students, an introduction to JUMP or to DOE, to your students. We are here to help. Please get in touch. And as I see, time is flying and we are over time. So Ross, I'm not running away. Happy to answer any outstanding question.
Great. Thank you, Volker, and thanks for this great review of so many different but very important advanced considerations when building these custom designs. This has been a particularly active Q&A, especially with the depth of the questions. So I think you've touched on a lot of things that people find very important and potentially useful. Everyone, Volker and I can stick around for a little bit here to field more questions as you might have them. So please do type them in the Q&A. Volker, while we wait to see if there are any remaining questions, somebody just asked one that maybe you can comment on briefly because it is a pretty wide consideration here, but it's generally just about model selection. So you create one of these experiments, you have some a priori model that you want to fit or effects that you want to estimate, but it's not always the case that that should really be the final model for, say, an optimization problem. Can you comment on maybe just where people should look in JUMP to help them choose which effects belong in the model and which ones don't?
Sure. So I would suggest the starting point, take the analysis script, the model script, which is added by the design tool to your design table. And sometimes there are also several options. So typically you find just a model script. And as I said, this corresponds to your a priori model you specified during the design. Yeah? Sometimes there are also some other more advanced modeling techniques. And one modeling technique to mention is a generalized regression. So here we see a generalized regression output with a solution path. Yeah? And this also does a validation. Yeah? It minimizes the AIC corrected, yeah, and picks the best model with the minimum AIC. And depending on the penalty and how you configure this method, it could also do some variable selection for you and more or less or semi-automatically simplify the model. So generalized regression is also highly recommended. It's not the standard, the default, but highly recommended and very, very useful in many experimental situations. Another mention is SVEM, SVEM, self-validating ensemble models. This is a very tricky way modeling very small experiments. Yeah, if you have many model terms you want to estimate, but you don't have enough data. So the SVEM algorithm, which is also built into the GenReg platform, this can do some magic for you by shuffling and copying the existing data and then building many, many models and then create an ensemble model using bootstrapping and ensemble modeling. And by that, you can estimate model parameters and or terms which are not estimable with a standard multiple regression or other modeling technique. It's really tricky, and it's a solution if you are in need of more data. But yeah, what can you do if you want to analyze and learn about all the curvature effects and you don't have enough data? SVEM, I think you can easily find some presentations, Jump, Discovery Summit talks, because this was really a big news and a great development a few years ago.